For years, Enceladus looked like a frozen afterthought. A small moon of Saturn, bright white, cracked with blue scars, quietly circling far from the sun. Then it started spraying water into space. Those towering plumes erupting from its south pole changed everything. They told us that beneath tens of kilometers of ice, there is a global ocean. Not locked away forever either, but actively venting its contents into space where spacecraft can sample it directly. That alone made Enceladus special. Now it is stranger than that. Scientists analyzing data from a spacecraft flyby have confirmed the presence of new organic molecules coming from that hidden ocean. These are not signals inferred from afar or blurry hints from a telescope. They are real chemical fingerprints captured as a probe flew through ice grains that once belonged to liquid water below the surface. The finding matters because organic molecules are the raw materials of chemistry that life uses. Not life itself, not proof of organisms, but the kind of carbon-based compounds that, given the right conditions, can participate in the long chain of reactions that biology depends on. What makes this moment different is how many of those conditions appear to line up in one place. Liquid water, energy from tidal heating, active chemistry. And now, a richer mix of organics than scientists expected to find so far from Earth. According to NASA, Enceladus is no longer just an icy moon with a subsurface ocean. It is a working chemical system, still evolving, still active, and still offering clues about how common life-friendly environments might be in the solar system. The idea that Enceladus hides an ocean did not come from theory first. It came from surprise. When a spacecraft flew past the moon in 2005, it detected jets of water vapor and ice blasting out of long fractures near the South Pole. These fractures were later nicknamed tiger stripes. Nothing about a small, icy moon should allow that much material to escape into space, especially at speeds high enough to form a vast plume. The simplest explanation was liquid water below the surface, under pressure, finding cracks in the ice and venting upward. But scientists did not stop there. They tested the idea from multiple angles. As the spacecraft passed close to Enceladus, it measured tiny changes in its speed caused by gravity. Those variations revealed that the moon's interior is not solid all the way through. Instead, there is a dense layer beneath the ice, consistent with a global ocean tens of kilometers below the surface. Thermal data added another piece. The South Pole is far warmer than sunlight alone can explain. The heat comes from tidal forces. As Enceladus orbits Saturn, it gets stretched and squeezed, generating internal friction that warms the interior and keeps water from freezing solid. Then came the clincher. The plumes themselves contain salts and tiny silica grains. These are not products of surface ice. They form when liquid water interacts with rock at elevated temperatures. In other words, the ocean is not just sitting there, it is chemically active and in contact with a rocky seafloor. Put together, the evidence leaves little room for doubt. Enceladus is not an ice shell hiding a static pocket of water. It is a world with a long-lived global ocean that is still moving, still warm, and still connected to the surface today. The discovery did not come from a new mission or a new flyby. It came from taking a deeper look at data that had been sitting quietly for years. As a spacecraft passed through Enceladus's plumes, it collected microscopic ice grains and vapor. Embedded inside those grains were chemical clues from the ocean below. At the time, scientists could identify simple organic compounds, small carbon-based molecules. Interesting, but not unexpected. What changed was the analysis. Using improved laboratory techniques and a better understanding of how ice grains fragment when they hit a detector at high speed, researchers realized something had been hiding in plain sight. The data pointed to much larger and more complex organic molecules than previously confirmed. These were not single carbon compounds or short chains. They were heavy organics with masses suggesting structures made of dozens of atoms. The kind of complexity you usually associate with environments rich in chemistry, not a tiny moon in the outer solar system. According to NASA, the molecules likely formed in Enceladus's ocean itself, not on the surface and not from contamination. The ice grains acted like frozen messengers, carrying samples of liquid ocean chemistry straight into space. What makes this finding stand out is how it was detected. The spacecraft did not drill through ice or land on the surface. It simply flew through a plume and let physics do the work. Each impact shattered a grain and produced a chemical signature, allowing scientists to reconstruct what had been inside. In other words, these complex organics were not inferred indirectly. They were measured. And they came from a place where liquid water, heat, and rock are interacting right now. That combination is rare, and it is exactly why this result has shifted Enceladus from an interesting ocean world to one of the most chemically promising places we know beyond Earth. Organic molecules are often misunderstood. They are not a sign of life by themselves. They do not mean cells, organisms, or biology is present. What they represent is chemical potential. At the simplest level, an organic molecule is just a structure built around carbon. Carbon is special because it bonds easily with itself and with other elements, forming long chains, rings, and complex frameworks. That flexibility is why life on Earth uses carbon as its backbone. But not all organics are equal. Simple organics are easy to make. They can form in cold space, in comets, or even in interstellar clouds. Complex organics are different. They require environments where chemistry has time, energy, and repeated interactions to build larger structures from smaller pieces. That is what makes Enceladus interesting. The newly confirmed molecules are large enough to suggest multi-step chemistry. Reactions happening over time in liquid water, possibly driven by heat coming from the rocky seafloor below the ocean, similar in principle to hydrothermal systems on Earth. On our planet, environments like that are thought to have played a role in prebiotic chemistry. Not life itself, but the processes that make life possible. Concentrating molecules, cycling energy, and creating conditions where complexity can increase rather than break apart. The key point is not that Enceladus has the same chemistry as early Earth. It almost certainly does not. The point is that it has crossed an important threshold. It is not limited to simple background organic compounds drifting in from space. Instead, it appears capable of generating and sustaining complex organic chemistry internally. That moves Enceladus into a different category. Not just a moon with water, but a place where the ingredients and the environment can interact in meaningful, evolving ways. In astrobiology, that distinction matters more than any single molecule ever could. Enceladus forces a quiet rethink of where life might arise. For a long time, the search focused on planets like Earth. Solid ground, sunlight, and surface water felt essential. Enceladus breaks that pattern. No atmosphere to speak of. No sunlight reaching the ocean. Just ice, darkness, and chemistry doing its work below. And yet, the pieces line up in a way that is hard to ignore. Liquid water has been stable for a long time. Energy is constantly supplied by tidal heating. The ocean interacts with rock, allowing minerals and heat to drive reactions. Now we know that complex organic molecules are part of that system. Not delivered once, but likely produced continuously. That combination is what scientists mean when they talk about habitability. Not comfort, not familiarity. Just whether chemistry has enough room to get interesting. The implication reaches far beyond one moon. If Enceladus can maintain this kind of environment, then other icy worlds may be doing the same. Moons like Europa, Titan, and even distant ocean worlds around other stars start to look less exotic and more like variations on a common theme. What makes Enceladus especially compelling is accessibility. Its ocean is not sealed away forever. It is venting into space right now. That means future spacecraft would not need to land or drill through ice to sample it. They could simply fly through the plumes again, with instruments far more sensitive than before. According to NASA and ESA, ocean worlds are becoming a top priority for future exploration. Enceladus is no longer a side story, it is a test case. Not for finding life tomorrow, but for understanding how often nature builds environments where life could begin at all. What makes Enceladus unsettling in the best way is how ordinary the chemistry starts to feel. No rare miracle, no special timing, just water, rock, heat, and carbon doing what those ingredients tend to do when they are left together long enough. For decades, life elsewhere felt like a distant question tied to planets like Mars or worlds orbiting other stars. Enceladus shifts that perspective inward. It suggests that biology does not need a surface or sunlight or even a planet. It needs chemistry that can keep going without being shut down. The moon is small. Its ocean is buried. But it is active right now, venting samples of its interior into space. That means the question of habitability is no longer abstract. It is drifting past us in the form of ice grains and vapor, carrying the results of reactions happening far below an alien sea. Even if Enceladus never hosted life, it tells us something important about the universe. Complex chemistry is not fragile. It does not require perfect conditions. It emerges wherever physics allows water, energy, and time to overlap. And once you accept that, the number of places worth looking grows very quickly.